So our plan for today is to go as many possible examples as possible, right? So basically try to get used to, again, kind of going through the Lagrangians and coming up with the equations of motion, as well as getting used to these ideas of generalized coordinates. And also talk about degrees of freedom. I didn't really mention that, but degrees of freedom are basically equal to the number of generalized coordinates, but we'll talk more about that as we go through. So our first example we're going to look at is, so here I have a simple pendulum where I've expressed it in this Cartesian coordinate system. So here's the y-axis and then here's the x-axis, so that the pendulum is at the origin here. And what I want to do is express the kinetic energy and the potential energy of this simple pendulum in this coordinate system, in this rectangular coordinate system with x and y, our Cartesian coordinates, and then also find the Lagrangian, and then from there we want to find a coordinate transformation which then transforms the x and y coordinates to basically into plane polar coordinates, where we're probably only looking at theta, where theta then will be our only generalized coordinates, as we'll see. So we have 1 degree of freedom, and then from there we want to solve to determine the equations of motion from here. Good. So let's do that. So good. So in this case, since it's moving in the xy plane, so in this case we know that the velocity. So yeah, we'll write it this way. So the velocity then is simply going to be x dot in the I hat direction plus y dot in the j hat direction. Good. Which means our kinetic energy then, which is 1/2 mv squared, is simply going to be equal to 1/2 the mass times x dot squared plus y dot squared. Our potential, if we take this as our y is equal to 0 location, right? Our potential energy then is going to be equal to minus mgy, where y is simply the distance that this thing is down from here. So this is going to be our y. So good. So this is then our kinetic energy and our potential energy, which means our Lagrangian in our rectangular coordinate system is then simply going to be 1/2 m times x dot squared plus y dot squared minus mg, actually plus mgy in this case. Because remember, the Lagrangian is equal to the kinetic energy minus the potential energy. Good. So now we want to convert now to our theta coordinate system. So now we want to find a coordinate transformation that's going to allow us to do that. And that coordinate transformation we're going to get is simply we're going to read off of here. So for example, we can see that x then, the location that this thing is along the x-axis, is then going to be simply equal to L times then sine of the angle. Y then is going to be equal to what? Well, this is in the negative direction, so this has to be a negative sign, times L times then cosine of the angle. So from here, we can take derivatives of these guys. So this is going to give me x dot, and then is equal to, well, L is simply a constant, right? This simple pendulum has a fixed length. So that derivative is going to give me 0. Derivative of sine then is positive cosine. So this is then going to be, what? L times theta dot times then cosine of theta. Right? And I have to put theta dot in there because my angle is changing with time. Right? So from here we then get y dot, then is going to be equal to L times theta dot, where in this case the derivative of cosine is negative sine. So that's going to give me then sine of theta. Good. So putting these into these expressions, that means then the kinetic energy then is going to be equal to 1/2 the mass times, in this case I'm going to get an L squared with an L dot squared. So that's simply going to be an L squared times a theta dot squared. And then I'm going to get a cosine squared plus sine squared, which means that that's simply equal to 1. So my kinetic energy then is equal to 1/2 ml squared times x dot squared. Then my potential energy then is going to be equal to, so in this case I get a minus m times g, which gives me another minus, that's going to give me a plus, times L times cosine of theta. Good. So ultimately, this tells me that my Lagrangian then in this particular coordinate system is 1/2 m times L squared times theta dot squared. And then I'm going to get a minus mgl cosine of theta for this guy. Do I want to put that negative sign in there? Because it's already minus y is that guy. Yeah, sorry, this should be a plus, and this guy should be equal to minus, right? Has to be minus because it's still down in this particular direction, right? So I still need that negative sign there. Good. So basically, under here, this is showing that what? If I'm working in Cartesian coordinates, I have 2 degrees of freedom because I need to know what x dot is and y dot is and what y are, which basically means I have 2 coordinates at which I am paying attention to, which means I have 2 degrees of freedom. So in my rectangular coordinate system, I have 2 degrees of freedom. However, if I make the transformation then into my y, or into plane polar coordinates, we see that we actually really only have 1 degree of freedom. And the reason for that is that x dot and y dot, meaning that x and y, are actually not completely independent from each other, because this thing has to move along this fixed length of L. So basically meaning that here there's actually going to be constraint that I would have to put into here to actually be able to solve this, which I haven't put in, which means that overall, even here and here, there's only 1 degree of freedom, which means that it's actually easier to work here because I already have that degree of freedom basically built in. So good. So now to get the equations of motion, I'm now going to just take the partial of this guy with respect to theta minus then d dt of then a partial of the Lagrangian with respect to theta dot. Set that guy equal to 0. Taking respect to theta, the first term is independent of theta, so I only have the second term. So we get then a negative mgl sine of theta minus then the time derivative of then derivative of him. So this is going to give me then simply an m times L squared times theta dot is then equal to 0. So basically those are going to cancel each other, at least the negative signs. So ultimately this thing is going to give me that of a simple pendulum. So in this case the m's are going to cancel, right? One of these l's are going to cancel. So ultimately this is going to give me then what? Theta double dot from the second derivative plus g divided by L times sine of theta is equal to 0, which is what we should get for a simple pendulum. So again, in this particular problem, again, it appears if we work in our Cartesian coordinates, we have 2 degrees of freedom, but again, this thing has to be swinging something like this, which means it has to be on an arc, which means that these aren't independent coordinates. They're actually linked to each other by a constraint, even though we didn't write the constraint down. So if we make this proper transformation to plane polar coordinates, we see that there really is only 1 degree of freedom. So in this case, our generalized coordinate that makes this as simple as possible is actually then just theta. So let's do another example. So next example says that we want to consider the motion of a particle moving only under the influence of gravity in a 2-dimensional space. So basically projectile motion. And we want to do this in Cartesian coordinates as well as plane polar coordinates, basically just to contrast the two and then see which one would actually be easier to work with, which I'll tell you now will be Cartesian coordinates. So, great. So in this case, again, what we know is what? If we had an object moving something like this, give it some initial velocity in this direction. So that means that it has a velocity x dot this way. It's going to have a velocity y dot this way, which means v then is going to be equal to, again, x dot in the I hat direction plus y dot in the j hat direction, so that the kinetic energy is exactly the same as what it was in the previous problem. It is simply 1/2 m x dot squared plus y dot squared. And then here we're saying that this is the y direction, this is the x direction. So in this case, gravity we know is going to be equal to what? Simply mgy, where we're defining that wherever the ground is our y is equal to 0 location. So good. So from here, we then have that our Lagrangian is then equal to 1/2 m times x dot squared plus y dot squared minus mgy. Now from here, again, we have 2 degrees of freedom. Our 2 degrees of freedom are x and y. Right? So this thing is moving in the x and y direction. So there are actually 2 degrees of freedom. So in this case, we then have to define the equations of motion. We then have to take the derivatives in respect to both x and y. So we're going to have 2 different Lagrangians, or at least equations of motion, one for the x direction and one for the y direction. So let's look at the x direction first. So for the x direction, we have the partial Lagrangian with respect to x is simply equal to 0, which means that our equation of motion is going to become 0 is equal to simply what? The derivative with respect to time of then the partial of this with respect to x dot, which is then equal to, so it's going to be the time derivative of then simply the mass times the velocity. So just the momentum, which in this case says that the momentum in the x direction is actually conserved, so the momentum doesn't actually change. So taking our derivative of this, we get simply the acceleration is equal to 0, right? Because we get mx double dot is simply equal to 0, which means our acceleration is 0. So we have no acceleration in the x direction. In the y direction, that's not going to be true, because now when we take the partial with respect to y, we're simply going to get this guy. So here we take the partial with respect to y minus the derivatives with respect to time of the partial with respect to y dot, set that guy equal to 0. So here I'm going to get a minus mg minus then a. Take the partial of this with respect to y dot. I'm going to get simply an my dot. This is going to be then my double dot is then equal to 0. M's are going to cancel, so this means then that what? Y double dot is simply equal to minus g. So the only acceleration that this thing is feeling in the y direction is the acceleration due to gravity, which again has to be true. We already knew that. So good. So everything here goes with exactly everything we talked about way back when, even in Physics 205, in the fact that, what, if we have projectile motion, something moving, there is no acceleration in the x direction because it's not moving in a fluid. And the only acceleration it has then is in the y direction. So this gives exactly the same results that we should have had then. Now, here, now we want to work in polar coordinates. So let's now do exactly the same thing, but now in plane polar coordinates. So good. Plane polar coordinates, kinetic energy becomes a little more complicated, because now we have to work in plane polar coordinates. So it's going to be 1/2 the mass times r dot squared plus r squared times theta dot squared. So this is now our velocity term. In this case, the y direction then is going to be what? So this is now going to point for r, so r is going to be off in this direction. So let's say our particle is sitting here, so this is our r, this is the angle of theta, so that means that what, the y portion, so u then is going to be mg times y, but y then is going to be the same thing as r times sine of theta, right? So from here, we then get that our Lagrangian then is going to be equal to 1/2 m times r dot squared plus r squared times theta dot squared minus mgr sine of theta. So again, we have 2 degrees of freedom, meaning we have 2 generalized coordinates. In this case, our generalized coordinates. So our generalized coordinates are then going to be simply r and theta. So in this case, our generalized coordinates are r and theta. So again, since I have 2 generalized coordinates, what that means then is I have to consider the equations of motion in both of those 2 different directions, which means we have a equation of motion in the or in the r direction as well as in the theta direction. So let's do the r direction first. So good. So here for the r direction, we're going to get what? The partial of Lagrangian with respect to r minus then the time derivative of the partial of the Lagrangian with respect to r dot is all equal to 0. So I take the partial with respect to r. I have two terms which are dependent on r. So this one is going to give me a what? M times r times theta dot squared. And then I also have this term, which is going to give me a minus mg times sine of theta. And then I get my minus my time derivative of respect to r dot. So in this case, I only have one r dot term. So this is going to give me an m r dot is equal to 0. So again, all the m's are going to cancel. So I don't care about the m's. So good. So finally, what I get then is what? Minus r double dot. Right? And then I get a plus r theta dot squared minus g sine of theta is equal to 0. So this is my r equation. Not very pretty, but it's my r equation. And now let's look at the theta direction. So for my theta direction, again, we now have the partial of Lagrangian with respect to theta minus the time derivative of the partial of the Lagrangian with respect to theta dot, again, is all equal to 0. So theta, there's only one term that depends on theta, and that's this guy. So I'm going to get a minus mgr times cosine of theta, right? Because derivative of sine is cosine. Then I'm going to get a minus time rate of change of. So in this case, there's only one term that depends on theta dot, and that's this term. So this is going to give me then a what? M times r squared times theta dot. Because again, that 1/2 is going to go away from that derivative. And again, all this is equal to 0. So in this case, this is now going to give me a little bit more complicated because now, remember, both r and theta are both time dependent, as opposed to here where I only had one time dependent object. Here I now have two time dependent objects. So now this is going to give me a minus, well, let me get rid of the m's, because again, the m's are all the same, so I cancel out that m. So I'm going to get a minus g times r times cosine of theta minus, so now if I take the derivative of the first term, that's going to give me a 2r dot theta dot minus r squared times theta double dot is equal to 0. I'll just leave it this way. Great. So to solve this system, we now have what? Two coupled equations, right? Because now the solution for r double dot depends on the solution for theta dot, but the solution for theta double dot depends on the solution for r dot, which means these are now two coupled equations. So for me to solve this, I would actually have to uncouple the equation, which may take a little bit of work, right? So this is actually a good example where, again, depending, no matter which generalized coordinates we chose, where in the first case we chose x and y as our generalized coordinates. So in that case, we ended up with two simple solutions that we had to solve for. We got that simply, what? X double dot was equal to 0, so there was no acceleration, meaning that, as we saw, momentum was conserved. And in the y direction, momentum was not conserved because there was a force in that particular direction. But in that case, we had two simple expressions. We had to solve x double dot was equal to 0 and y double dot was equal to negative g. But here, if we work in a different coordinate system, in this case plane polar coordinates, again, we still have two generalized coordinates, r and theta, but now when we're trying to solve our system, we have now two ugly expressions that we have to solve, which, as we just mentioned, are coupled equations, so we have to uncouple them to actually finally solve them. So even though this is a valid way of solving it, it's probably not the ideal way because it doesn't lead to something which is simple, right? Which is something we talked about in the previous video, where the best generalized coordinates we can use are going to lead to something which leads us to solving simple, which in this case the plane polar coordinates is not the right choice then. So let's do another example. So the next example says that we have a particle of mass m is constrained to move inside of the surface of a smooth cone of half angle of alpha. So here is my cone, and this thing has an half angle of alpha, and my particle is going to move around basically inside of here. Okay, so it's constrained to move inside of the surface. Okay. So from here, I want to determine, again, what are my generalized coordinates? So generalized coordinates. And then from there, determine the constraints. So the constraints will actually determine the number of generalized coordinates that we actually have. So that'll restrict the number. And then finally, we want to find the equations of motion for this particular situation. So one thing to notice is what? For any radius that this thing is basically moving with cylindrical coordinates, right? So for here, the easiest thing to do is choose our generalized coordinates to be cylindrical coordinates. So first off, we're going to choose our generalized coordinates then to be what? So let's call this r, theta, and z. Okay. So what about our constraints? Well, our constraints are that what? R and z are not independent from each other. And we can see that's because, right, if this is our radius of r, right, this is our height of z. In this case, what I know is that what? R divided by z is the same thing as tangent of that angle, right? So I get that tangent of alpha then is equal to what? R divided by z, which means that our equation of constraint, grz, which is equal to 0, then is equal to r minus z times tangent of alpha. So this is my constraint equation, which again basically just tells me that's what? Z and R are not independent from each other, which means that ultimately there's only going to be two generalized coordinates. So either I can express my system in terms of R and theta, or in terms of theta or z, but ultimately because of that constraint, even though I originally started off with 3 generalized coordinates, I have one constraint equation, which means that we actually only have 2 generalized coordinates, which then forces us to have 2 generalized coordinates, i.e. 2 degrees of freedom. So degrees of freedom are equal to the number of generalized coordinates that we actually have. Good. So in this case, we can choose which one that we actually want to get rid of. We'll do that in just a second. Good. So first things first is we know the velocity squared is going to be equal to r dot squared plus r squared times theta dot squared plus z dot squared. Because again, this is our plane polar coordinates. The velocity plus then the velocity in the z direction. Good. Now in this case, we have to make a choice. How are we going to represent our system? So the choice I made is I'm going to represent this in terms of these 2 generalized coordinates. So r and theta, which means that I'm going to replace z with r. So from here, which again tells me that's what? Z times tangent of alpha is equal to r. Then this tells me that's what? Z dot is then equal to r dot divided by tangent of alpha. Right? So this is going to be the same thing then as what? R dot squared times 1 plus 1 over tangent squared of alpha plus r squared times then theta dot squared. Right? So again, this thing is now just going to become an r dot squared over tangent squared. But that's the same thing as what? Cosecant. So it's going to be r dot squared times cosecant squared of alpha plus r squared times theta dot squared. Good. So this is our velocity term. Our potential energy then is, well, let's go ahead and call this then, oh, sorry. So one thing I should mention is I'm actually calling this my z direction. So let's take this as x, let's take this as y, so this is our z, which means that our potential is equal to 0 at the origin. And since our particle is sitting here at z, then that means our potential energy is then just going to be mgz, which is going to be the same thing as mgr divided by tangent of alpha, right? Tangent of alpha, which is the same thing as mgr times cotangent of alpha. So good. So from here, we finally get our Lagrangian then is going to be equal to 1/2 m times r dot squared times cosecant squared alpha plus 1/2 m times r squared theta dot squared minus mgr cotangent of alpha. So this is our Lagrangian. Okay, our Lagrangian has two generalized coordinates, which means that we have to find two separate equations of motion. So in this case, we're going to find one equation of motion for the r direction and one equation of motion for then the, pardon me, the theta direction. And then we'll have to solve these two simultaneously if we wanted to know the actual path of the particle. But again, for now, we just want to know the equations of motion. So again, let's start off with the r direction. Let's do that one first. So that says that we take the partial of the Lagrangian with respect to r minus then the derivative of the partial of the Lagrangian with respect to r dot. Set that guy equal to 0. So from here, there are two terms which depend on r, which means that this is going to give me m times r times theta dot squared, right, from that first kinetic term, minus mg times cotangent of alpha, because that r portion is just going to go away, minus the time rate of change of the derivative with respect to r dot. So here there's only one term that depends on r dot, which is this term, so this is going to be m times r dot times then cosecant squared alpha, and all that's equal to 0. Again, all the m's are the same, so we can cancel out the m's, we don't have to worry about those. So finally, we're going to get, for the r equation, we're going to get r times theta dot squared minus g times cotangent of alpha minus r double dot times cosecant squared alpha is all equal to 0. Good. Now again, this is a coupled equation just like before. So now the solution for r double dot depends on the solution for theta dots. Good. So now let's look at the theta equation. So good. So let's do the theta equation. Now, first thing to notice is for the theta equation. So for theta equation, or theta direction, in this case, but nothing here that actually depends on theta, which means the partial derivative with respect to theta is actually just equal to 0, which means in this case we have to have the time rate of change of the partial of the Lagrangian with respect to theta dot must be equal to 0. So only one term actually depends on that. So this says that the time rate of change of m times r squared times theta dot is simply equal to 0, but mr squared times theta dot is simply the angular momentum, right? This is the moment of inertia times the angular velocity, so this is just the angular momentum. So here all this says then is that the angular momentum, the derivative of that must be equal to 0, which is just conservation of angular momentum. So here, in the theta direction, just means that as this thing is spinning around, whether it's at a bigger radius or at a smaller radius, the angular momentum is simply conserved. Right? That's all this thing is saying. So from here, we can easily then solve this, right? Because this just says that the angular momentum is equal to a constant. Plug that back into here, which means that this term is actually then just constant, so we can actually solve this actually rather easily in this case. Good. Let's do another example. much chalk dust flying around in the room. The things I do for you guys. All right, anyways. So, next example says that we are going to have a massless rim of radius A. So here's my rim of radius A. And then attached to a point here on the rim of the A is then a simple pendulum, which has a length of B, and then has a mass M at the end of it. Okay? And then this rim is going to be rotating around with a constant angular velocity, omega. So this guy is simply equal to a constant. So here we want to obtain an expression for the Cartesian components of the velocity, the acceleration, and of the mass, and then obtain the angular acceleration for the angle of theta. Okay. So what's theta going to be? So theta is going to be this angle here, which is the angle away from the vertical at which this simple pendulum is then swinging around. Okay. So basically what's happening is this thing is undergoing superharmonic motion, but this wheel is rotating about the center of mass location, which means that it's swinging, but this thing is rotating, which is going to cause this weird kind of funky rotation. So good. So let's set up a coordinate system. So here I'm going to choose this as my x and y directions. Okay. And we know that this thing is rotating with constant angular velocity, which means that this angle here is simply going to be omega t. So if I want to describe the motion of this point here, so in the x direction, that's going to be this distance here, plus then this distance here. Right? So for the x direction, what I know is that x is going to be equal to a times cosine of omega t, right? Because that's just this portion, plus this portion then. So this is then going to be what? The sine portion then of b. So it's going to be b times sine of the angle theta. Y then is going to be what? This portion here plus this portion here. Right? So in this case, this is going to be a sine of omega t minus, right? Because overall I'm going to subtract from there that particular point. Actually, sorry, minus this point. So this is going to be then, no, I'm sorry, the first time. So minus that entire thing. So it's going to be minus then b cosine of theta. So from here we can find the velocities. So take the derivative of these. So I get x dot then is equal to, so here I'm going to get a cosine, so it's going to be a negative a omega sine of omega t. Right. Derivative of this guy, b is also a constant, so I'm going to get a minus b times theta dot times cosine of theta. Derivative sine, sorry, positive. There we go. Y dot is then going to give me equal to a times omega times cosine of omega t. And then I'm going to get a plus, because the derivative of cosine is negative sine. So plus b times theta dot times sine of theta. So these are my velocities. Good. Now from here, we can find the acceleration in the x direction. So my acceleration in the x then is going to be equal to another derivative of this thing. So again, a is constant, omega is constant, so I'm only going to take the derivative of that. So I'm going to get a cosine, so I'm going to get a negative a omega squared cosine of omega t. And then here now I have two terms, so I have to take the derivative of this one and then the derivative of this one. So I'm going to get a plus b theta double dot, and then I'm going to get a times cosine theta minus b times theta dot squared. I'm going to get an extra theta dot from here, times then sine of theta. And then finally y double dot. So again, everything here is constant except for the cosine, so I'm going to get a negative a omega squared sine omega t. And again, here I have product of two functions. Okay. So I get a plus b theta double dot. Horrible double dot. There we go. Double dot times sine of theta plus b times theta dot squared times then cosine of theta. Right? Now, viewing all of this, we can basically see again is that what? A is constant, omega is constant, B is constant. The only thing that's not constant is theta, which means that there's only one generalized coordinate in this case. That one generalized coordinate is simply him, so this is actually my generalized coordinate. So this whole entire system is boiled down to simply knowing what theta is doing. Once I know what theta is doing, then I know exactly everything about the motion of this particle. So good. So finally, we can then write the Lagrangian and write the kinetic energy and the potential energy. Well, I should erase that part, but let me keep this part first. So from here, we can now write the kinetic energy. So our kinetic energy then is going to be 1/2 the mass times x dot squared plus y dot squared, which means that I'm going to square each one of these guys and simply put them in. It's basically going to be a big mess, but you'll see that some terms will end up being squared, so they'll actually cancel with each other. So this thing actually simplifies to, so let me just write down the answer. So 1/2 m times a squared omega squared, so that's by squaring this guy, adding to the square of this guy. This guy squared with this guy squared, so again that's going to be 1, so it's going to give me a plus b squared times theta dot squared. Now we have the cross terms to worry about, so then we get a plus 2ab times theta dot times omega times sine of theta minus omega t. So here I'm using a double angle formula because here when I look at the cross terms I'm going to have a sine of omega times cosine of theta and then cosine of omega sine of theta. So I'm just using a double angle formula which reduces to this. Minus my potential energy term. So let's write down our potential energy. So we can finally get our equations of motion. Good. So good. So our potential energy then is going to be equal to what? So in this case, minus mg y. So this is going to be equal to then what? Minus mg times the y, where the y was the same thing as what? So I had an a sine of omega t. Make that positive. Minus then b cosine of theta. Good. So finally, our Lagrangian then is simply going to be t minus u. So basically just the sum of those two things. So finally we want to do is obtain our equations of motion. So again, we want the partial of the Lagrangian with respect to theta. So here, that's going to have two terms in it, right? We're going to have a term from here as well as a term from here, because this is a theta dot, this is also a theta dot, but we do have that theta to worry about. So if I take the partial of this with respect to theta, it's going to be MAB theta dot omega times then cosine of theta minus omega t. So that's just the partial of this one. So basically the only thing that's going to happen here is that sine is going to turn into a cosine. Yeah, and the 1/2 cancels with this guy. And then we also have the partial of L with respect to theta dot. So here there's going to be what? One term from here, one term from here, and that's it. Good. So this is going to be the same thing then as m times b squared theta dot plus m times ab times omega times sine of theta minus omega t, because in this case this theta dot is just simply going to go away. So finally, here we can now take a derivative of this guy. So let's write a total derivative of him, which means we need a time derivative of this guy as well. Okay. So again, here what's going to happen is m is a constant, b is a constant, so this is going to become a theta double dot. Here, everything here is constants except for the sine term. So again, we're going to get a theta dot out of that with a cosine term. It's going to become a negative. So putting everything together, we finally get then is what? Our equations of motion. in terms of just this one generalized coordinate, which in this case is theta, ends up being, so we finally get theta double dot is equal to a times omega squared divided by b cosine of theta minus omega t minus g divided by b times sine of theta. So this is then my equations of motion for this guy. Now one thing to note is if we let omega go to 0, so for example, if we weren't having this ring actually rotate, if it was at a fixed angular velocity, what will happen then is this term is going to go to 0, which means we reduce down to theta double dot is equal to simply g divided by b times sine of theta, which is that of our usual simple pendulum. So this thing actually reduces properly to what we should have if this thing wasn't doing that weird rotation. Okay. Good. 2 more problems to go. And then I can get out of this room with this chalk dust for a little bit. Until I make another video in like 2 minutes. Live over here. So the next one says that we're going to have a bent ring, or at least a bent wire, which is in the shape of a parabola, which basically means that, again, if I call this my z direction, then z is equal to some constant times r squared. We're simply calling this direction here the r direction. So that's effectively saying that this is the x, this is the y, but this distance across here is what we're going to call r. Now we're going to put a bead on here. So here's my bead, which has a mass of m. But we're going to cause this thing to rotate basically around in a circle with a angular velocity of omega. Now, what we want is for this bead to be at some height, z here, with some radius of r, and be here fixed at this particular radius of r. So basically what we want to do is we want to set little r equal to big R, which is going to be some sort of constant. And what we want to do in this case then is determine, well, what is c? What exactly is c? So, same thing as we did with the other problem, we can see is what? When this thing is rotating about this particular radius here, this thing has cylindrical symmetry to it, which means that, again, our generalized coordinates we can use are those of just cylindrical symmetry. So again, our generalized coordinates we're going to choose in this case are going to be, again, r, theta, and z. Our constraint in this case is simply this guy. So again, we have a constraint, which goes as g of z and r, which is equal to 0, which is then equal to z minus c r squared is equal to 0. So again, same thing we had in that previous problem. What's happening is even though I have 3 generalized coordinates, only 2 of them are independent because z in this case depends on r, or r depends on z. So again, that means we can rewrite our entire function here, or at least everything in terms of the 2 generalized coordinates, either r and theta or theta and z, because nothing is dependent on theta, so theta is truly an independent quantity. So good. So here we have the same kinetic energy we had before. That's simply equal to 1/2 the mass times r dot squared plus r squared times theta dot squared plus z dot squared. Right? This is still the same. Potential energy, again, if this is some height of z, again, we know the potential energy is simply mgz. So here, again, we have to make a choice on how we want to represent this. Here, I'm going to use, again, r and theta instead of theta and z. So I'm just going to rewrite all my z's in terms of my constraints here. So that means this is going to be the same thing then as 1/2 m times r dot squared plus r squared theta dot squared. Plus, so that guy squared, that's going to give me a 2cr dot. Okay, that's going to be that guy. And then this guy is going to be equal to mg c times r squared. So let's put everything together. So our Lagrangian then is going to be equal to 1/2 m times So we're going to get an r dot squared times 1 plus 2 times c, right? That comes from combining these two terms, plus r squared times theta dot squared. So that is our kinetic energy part, minus then our mgc times r squared. So in this case, we actually have, what, two generalized coordinates again. We have theta and we have r, even though we technically only have one, and the reason for that is we're going to set r is equal to capital R, so that's going to go away, so that's actually not going to be a generalized coordinate, because that's going to be a fixed value, so everything's going to be defined in terms of simply theta, so the angle around here. But for now, let's work with both directions, just for funsies. So good. So again, let's do the r equation. So for the r equation, again, we're going to take the partial of this with respect to r. So we get the partial of L with respect to r, minus then the time rate of change. The partial of L with respect to r dot is equal to 0. So here, again, we're going to get what? So we have two r terms. We have this term and this term. So this is going to be the same thing then as what? M times r times theta dot squared, right? That's that term, minus, so this is going to give me a, what, 2 mg times c times r, minus then the time rate of change of, so now when I take the r dot, only one term depends on r dot, which is this term, so this is now going to give me a m times r dot times 1 plus 2c. Okay. And all that's equal to 0. So this is our r equation. Now we can look at our theta equations. Let me get rid of this top part here. Now notice again when we do the theta equation, what's happening in this case then is what? Nothing depends on actually theta, which means that this first term is actually going to be 0. Which means for the theta direction, or for the theta equation, we're going to have then that simply the time rate of change of the partial with respect to theta dot is equal to 0, which is equal to the time rate of change. Well, only one term depends on theta, and this is mr theta dot squared. Oops, sorry, r squared theta dot, which again is simply equal to the angular momentum. So again, the theta direction simply gives us conservation of angular momentum. That's it. So the only useful piece of information we got out of there is that the angular momentum is conserved. Which is okay. So again, going back to here, this actually gives us two coupled equations. This says what's happening in the r direction depends on what's happening in the theta direction. But again, here we know that little r is actually equal to capital R, which is actually simply equal to a constant. So when that's true, that implies that r dot is equal to r double dot, which is equal to 0, which basically means that what? This whole entire term is actually going to be equal to 0, which actually simplifies our problem because now the m's are going to cancel. We're simply going to get that capital R times theta dot squared must then be equal to 2g times c times capital R, or that gives me capital R times then what? Theta dot squared minus 2 times g times c must be equal to 0, right? So in this case, we want to solve for c, but this thing is also moving, and it's moving with a constant angular velocity, which is actually the same thing as theta dot. So theta dot here is actually the same thing as omega, so this is actually omega squared minus 2gc. When this thing is equal to 0, that means what? This portion in the parentheses must be equal to 0. So this tells me c then has to be equal to omega squared divided by 2g. So this is the factor of c, which is going to allow this thing to be moving at a constant radius with a constant angular velocity. Good. One more to go. Down for a second. after the semester is over, I really need to clean out this room. There's so much chalk dust in here. It's a nice thick layer on everything. So anyways, the last one says that we have a double pulley system. We want to use the generalized coordinates, or at least the coordinates indicated, and determine the equations of motion. So let's draw the system. So basically what's happening is, say, here's the ceiling. This is the ceiling. And then here I have a pulley. So here's my pulley attached to the ceiling. And we're going to pretend that these pulleys are massless. Okay, so this is a massless pulley. And then on this side, so this is an Atwood machine, basically. So over here, I'm going to have one mass of M1. But then this one is attached to a second pulley. So here's my second pulley. So this is attached at the center of mass. Where on this side I have, hanging down here, M2. And then hanging down on this side I have M3. Now in this case, what I know is that these two lengths of chords must be fixed lengths. So this one is going to have an L1 worth of fixed chord length, and this one's going to have an L2. And the coordinates that it wants me to use are, if this is the center of this pulley, then this distance here to the center mass of him is simply going to be x. So this is my coordinate x. And then if this is the center of this pulley, then the location to M2 is going to be y. Okay. Good. So these are the coordinates that it actually wants me to use. So in this case, we have to use these coordinates to determine everything from there. Now notice if this distance is x, and this has a total length of L1, then this distance from here to here is then going to be what? L1 minus x. So in this case, I'm assuming that the pulley is actually point size, so that there is no radius to it, so I don't have to worry about how much is actually wrapped around here. So this thing is actually just a point, because it's massless, so I don't care as much. And again, if this is a distance y, then this distance from here down to this location is going to be L2 minus y. So these are our positions. So from these, we can now determine the velocities, right? So basically, the velocity of the first object, so V1, is simply going to be x dot, right? This thing is moving down in this direction with a velocity of x dot. For this guy, for then what? V2, well, this is then going to be what? The total distance from here, because I'm taking everything in reference to actually this line. So what I know is the distance from here to here is going to be L1 minus x, plus the distance from here to here, which is then going to be x. So V2 then is going to be then the time rate of change of, L minus x. So L1 minus x plus y, which is the same thing then as minus x dot plus y dots. Okay. B3 then, so in this case, again, taking reference to this line here, this is my, say, y is equal to 0 location, right? Or just whatever I'm telling my coordinate system to be at, then this distance is going to be L1 minus x plus L2 minus y. So this velocity then is going to be ddt of then L1 minus x plus L2 minus y, which means its velocity then is going to be what? Minus x dot minus y dot. So these are all my velocities. So from this, I can write the kinetic energy. So my kinetic energy then is going to be 1/2 times. So in this case, yeah, let's do it this way. M1 times V1 squared plus 1/2 M2 times V2 squared plus 1/2 M3 times V3 squared. Right? They all have 1/2 in common, so I'm going to go ahead and factor out the 1/2. So it's going to be 1/2 times. So from here, this is going to give me an M1 times x dot. Good. And then I'm going to get a plus M2 times y dot minus x dot. And then finally, I'm going to get a minus M3 times x dot plus y dot. Okay, this is my total kinetic energy. So now that we have the kinetic energy, we can get the potential energy. I'll write that up here. So again, using this as my reference line, then the total potential energy is going to be the sum of these three potential energies. So they're all going to be negative because they're all down from here. So this is going to be simply equal to negative m1 gx, and then I get a minus m2 g times, so basically just this guy, so L1 minus x plus y. And finally I got minus m3 times g times L1 minus x plus L2 minus y. So this is then my potential energy. So both of these two things together, subtracted from each other, gives me my Lagrangian. So now, from here we can see that again we only have two generalized coordinates. Those generalized coordinates then are both the x and the y. Which means that we now have two separate equations of motion. We're going to have one equation of motion for the x direction and then one equation of motion for the y direction. So I don't need this anymore. Let me get rid of this. So good. So from here, we can finally find then our equations of motion. So let's look at the x equation first. So for the x equation, again, we're going to have the partial of the Lagrangian with respect to x minus then the time rate of change. I hate these chalk. Times the partial of L with respect to x dot is equal to 0. It's going to be a big, long, nasty equation, but anyways, life will be fine. So here, all the derivatives from here are going to come from the potential energy term. So from here, we want negative the potential, so we're simply going to multiply all this through by a negative sign, which is going to make all these guys positive. So there's an x here, and an x here, and an x here. So if I take all those derivatives, so in this case, I'm going to get 0 then is equal to, move the 0 to the other side. So it's going to give me an m1 g. In this case, partial derivative is going to give me a negative sign, so actually this should be negative. So minus m2 times g, right, because all the other terms are going to cancel. And then same thing here, this should give me a negative m3 times g. Oh, wait. So that's all the first term, and then I get a minus time rate of change of this guy with respect to x dot. So again, there are three x dot terms. So this term is going to give me simply a, what? Oh, sorry, this all should have been squared. Should have a squared here, a squared here, and a squared here. Okay. So that's going to make life a little bit more complicated. So this one is simply going to give me a m1 x dot. And then from here, when I square this out, I'm going to get a y dot squared plus an x dot squared. So this is going to give me a plus m2 times x dot, but then I'm also going to get a cross term, which is then a minus x dot times y dot with a minus 2. So I'm going to get a minus 2 times m2 y dot. That's going to be from that term. And then from that term, again, I'm going to get a negative sign. So I'm going to get a minus m3 x dot. Right. That comes from the first term. The second term, I'm going to get a plus y squared, but that y squared term is going to go away. But again, I'm going to get a cross term, which is then going to give me a minus 2m3 times y dot. So good. So let's put everything together. So this is going to give me the same thing then as m1 minus m2 minus m3 all times g. And then I'm going to get a minus. So let's do it this way. So all the terms with x dots, I'm going to get a minus m1 plus m2 minus m3 all times x double dot. Right? And then I get the y terms, I get a minus and minus, so I get a plus 2 times m2 plus m3 all times y double dot. Right? So this is my x equation of motion. So in this case, my x equation of motion depends on the acceleration in the x and in the acceleration for the y. Right? But again, those two things are in the same direction, even though I'm treating them as, what you would think of as x and y direction. So it just depends on the acceleration of both mass 1 and mass 2. Good. So good. Now we have that. We can now look at the y equation. So let's do the y equation. So again, I'm going to get 0 then is equal to, so I have the same thing. Now I'm just doing the partial with respect to y. So I do the partial with respect to y. Here I have 2 terms, not all 3 terms, because this one doesn't depend on y. So I have the partial with both of those. So that is going to give me a, what, positive m2g minus an m3g. So it's going to be the same thing as m2 minus m3, all times g, minus then the time rate of change of. So now I'm going to take the partial with respect to theta dot. So this term goes away. This term I don't have, so this is going to give me an m2y dot. But now I have the cross term, so it's going to give me a minus m2 times 2 times x dot. Comes from that term. Good, get rid of this now. And then finally from the last term, I'm going to get a minus m3 times y dot. That comes from squaring this term. Again, that first term is going to go away. Now I have the cross term, so I get a minus 2m3 times x dot. So putting everything together here, we get an m2 minus an m3 times g minus. So in this case, then I get a what? So I get an, this one I have a negative, it's also a negative, so this actually become a plus. So I'm going to get a 2 times m2 plus m3, all times the acceleration of the first mass, minus from here. So then I get a, what? m2 minus m3, all then times y double dot. So these are my 2 equations of motion that I would have to solve. Again, these are coupled equations. So here, what's happening in the x direction, again, depends on both the x and the y, and what's happening for, so again, this is for mass 1. For mass 2, what's happening for him depends on the acceleration of mass 1 and the acceleration of mass 2. So good, so these are some examples. So again, generalized coordinates. Again, we can choose pretty much anything that we want as generalized coordinates. Again, the typical rule of thumb is that we're going to choose generalized coordinates, which is going to make our expressions pretty much as simple as possible. But as you can see, a lot of times these things aren't really simple. A lot of times they're going to give me a couple of equations, but under certain conditions, like in a couple previous problems where we said the radius was equal to a constant, that will reduce our problem down and make it a lot easier for it to solve. Again, a lot of these times that we saw when we had something moving into theta, as long as the Lagrangian overall is independent of theta, that then gives us the fact that the angular momentum must be equal to a constant, which is conservation of angular momentum. And as I pointed out in that one projectile motion problem, in that case, it was independent of x, which meant, or Lagrangian was independent of x, which meant that momentum was conserved in the x direction. So we're going to talk about this basically towards the end, but this is kind of leading up to something that we should notice, is that whenever a Lagrangian is independent of something, that gives us a conservation law. This is what's known as Noether's theorem. We'll talk about Noether's theorem as we basically get there. Noether's theorem basically says that symmetry and conservation laws are the same things. So again, here we saw twice that the Lagrangian was independent of theta, which gave us conservation of angular momentum. Once we saw it was independent of x, which gave us conservation of momentum. So we'll explicitly talk more about this basically at the end, but keep this in mind that this is something we're going to talk about, that an added benefit of working with Lagrangians is it automatically gives us conservation laws. So if our system is independent of something, meaning that it has symmetry in that particular direction, that equals a conservation law.